So what we are interested in is to integrate the sediment routing system from the production upstream, the erosion part, a zone, so what's a transfer zone? It's a zone where you have no sedimentation, no erosion, but most of the time it's quite difficult to get something that is a pure transfer zone. And you arrive to the last zone that corresponds to the sedimentation area, okay, the sedimentary basin itself. And we will see that a lot of economic implications, and I will be briefly talking about that at the end. Okay, so I repeat the same thing. I will repeat it many times. So you have a picture of Stanley Schumm. So Stanley Schumm, for me, was I remember I was a student. It was in the early 80s and 70s and early 80s, and he published a book called System. It was in 1977, and he defined this very interesting kind of a three-zone domain in Earth surface. And honestly, I was very intrigued at that, and I tried to understand what he was figuring out, and mainly what corresponds to the transfer zone and be in past sedimentary system. Okay, so this afternoon I will show you at the top how it's possible to say this is an erosion zone. Okay, this is the zone of sediment production for zone. Okay, this is a sedimentation zone. So there are tools just looking at geomorphology, looking geological map and modern system where you can be able to do that. So this is what is so again, it's the catchment upstream, okay, a zone where uplift occurs. So to get erosion, you have to, in most of the time, a sedimentary uplift. And to get deposition, you have to have subsidence. It's mean lithosphere collapsing somewhere to be able to get a sedimentary trap, okay? And what we are interested in is really to have a global understanding of the erosion sedimentation budget and something that is the sediment production. And the key question is based on a cause of the perturbation of the system is how long, what's the way the system responds to that perturbation. Okay, so just a example. So what we call an exoraic system. Okay, so this is a concept that we will use a lot. So I have here the example of North America. Okay, so if you look at the North American system, is that huge mountain corresponds to the Rocky Mountains that uplift after 80 million years ago, and this is in some places still a place uplifting, in place the extension and the decrease, and you get a huge transfer zone that corresponds to the form 14, and the end sedimentation is the Mississippi Delta, the Gulf of Mexico, northern, and in front of the delta, what you have is a large deep sea fan. I will be back on that. It is the ultimate zone of deposition. Another point that I want to insist on is that there are another type of sediment routing system that corresponds to what we call endorheic system, and an example is located in Africa. This is what we call the Mega Lake Chad. Okay, so this is a place where you have erosion upstream. So, for example, here in the Okar, you get a transfer and a zone of deposition that corresponds to a former large mega 8,000 million years ago. Okay, and now it's just a little teeny lake. Okay, and talk about a local base level. Okay, and this local base level could be a lake, or this is the case, for example, in a famous place called Kalahari in Botswana, where the local base level is the groundwater naps of desert. So it's that you have adapting to a groundwater system. Okay, so this is something that is and very exciting when you see those huge mega fan adapted fitting with level that below the desert. So this is something unbelievable. And I insist on the point is that this is something that's much more geological times. Okay? So it means that those endorheic system, we got plenty of those in past geological time. Okay. This is the first point. The second point that I want to emphasize is that we will talk a lot about systems, okay? But we have to keep in mind that there are other sediments produced in the sedimentary basin, what we call oceanic sediments, okay? And when we talk about system, we have not only to integrate, even it's what we have to do and what we will do during this week. We will not talk about the other kind of sediments produced in the basin, what we call oceanic. You know that this is something that could be very important in terms of sedimentary volumes. So here, classical depositional profile from alluvial fan, shelf to deep sea system. And of course, you know that after silicilastic sediments, the sediments corresponds to carbonates, and carbonates, you can get them in lake, and you can get in an environment with maximum production in the photic zone. The third type of sediments in terms of volume corresponds to the evaporate that you can or in lake again, coals, phosphate related to dwelling, for example, here, glauconite. All those systems has to be integrated in the source to system for two major reasons. Some of them, and mainly the evaporates, might be controlled by the solute of the continental weathering, chemical elements of the weathering that can lead to the formation of evaporite or to change the water. So this is something that is very important. Okay, or for example, it can be the transformation of former silicilastic fine grains transform in the basin. So this is something that is important. So it means that we will talk mainly about systems, okay? So it means sediment coming from the erosion of but keep in mind that in our understanding, even this will be not the case this week, to all the sediments produced in the sedimentary basin And we will see this afternoon that talking about chemical weathering, it has a lot of implications about sediment protection. Okay, so to start discussing on modern system, just some problem of terminology. Honestly, I don't care. Okay, but the terminology is becoming more and more difficult, and just to show you, and I've no answer, recommend to say that, or that. So for example, detrital is becoming popular, so it's because of sediment tracing. And so for example, this word sedimentologists did not read it, so it means that it disappeared, and it's becoming more and more popular, and we talk about clastic. So for some people, detrital is only silicilastic, but for some people, this is all what is made of particles, could be carbonate, could be what you want. So it means that using those words, you don't know the point that we can discuss on the field. So we use also silicilastic, terrigenous, halogenic, all those words more or less famous, or in situ production, oceanogenics for the sediment produced in the system. So, and to use what you want, but be careful about the way you use it. And for example, using detrital, you have to have in mind that this is ambiguous based on the culture that you have. Is that only the silicilastic, or is that all that is made of particles? Is something important. Last point for me, and again, this is something that is a specific approach when I'm talking about routing system, is the transfer, production, transfer, deposition of sedimentary sediments for a given time. And so to think is more the integration through time. So this is again something that maybe you can disagree with, but just to make sure the way I use, and this is a point that we can discuss later. Okay, so what I want to use is the diversity of sourcing systems, both in modern environment and in past geological time. So this is something that is important. A couple of words about the Earth's relief. So you know that the sediment production will be controlled by Earth's relief, and I will show you that this changed a lot during geological time. So of course, but there are also other elements that could be relief that corresponds to boulders, lives, plateaus and domes, plains. I will show you that in a couple of minutes. So this is very important to know about them, to recognize them. And we have the same for the submarine relief, and I will show you that on modern systems, sure that everybody agree about what's going on. So the Earth topography, I don't care, and this one, I will remove it. Okay, so a point that is very important when you look at modern system is to have data in a very specific period of the Earth's history in terms of climate evolution, okay? So, I will discuss this point later. So this is, here I took a CO2 measurement in the ice of the Antarctica. And what is interesting, just looking at this, is that you know probably, and if you don't know it, this is something that is very important, and I will be back on that in a couple of minutes, that 6 million years, that corresponds to the lower middle Pleistocene boundary, we got a flash. And this major climate change is probably unique in geological history. And we got a forcing of eccentricity cycles, okay? And we got what we call the glacial interglacial. It's a very strong climate change. So you got that with the sixth last one. So if you look, what is interesting is that in yellow you get the interglacial and the glacial. And if you look, the duration of the glacial interglacial is not the same according to different sites. Okay. So if you look 600,000 years ago, it's dominated by the interglacial one. It's dominated by the glacial one. And what we have to look, it's the effect on modern of those climatic variations in terms of climate, sediment production, and sediment transfer. So really, what I want to discuss with you, you will see that we know few things, that there are a lot of things to discover, but just to show you that at the first order, the dynamic of modern sedimentary system is the fact that from 1 million years, we got 9 major eccentricity cycles, okay? Strongly in terms of with glacial, interglacial of different durations, okay? And what we will check, the last one, okay, what we call the Vexellian or Würm based on the terminology you have to look at, okay? So just to show you the example of the, so I found this one, so this is in sea level, but it would be better to get them in 018, but we don't care about that. Is you get the last interglacial. This is the modern interglacial period. So it means that what you have to have in mind is that we got for the last cycle around of interglacial and 90,000 years of glacial stage. Okay, so it means that it's something that will have a twin source-to-sink system that is very, very important. So it means that even the cause is a cyclic variation of the insolation. The result, you know, probably because of the growth of the Laurentide ice cap, okay, you get something asymmetrical, and the end is that the duration of the glacial stage is much more than the interglacial one, okay? So this is something important, and we will check for all the 4 different modern sink systems that we have to look at, what could be the effect of this perturbation of on the system. Okay, so I repeat, this is something that is very specific in terms of dynamic. Just to show you this picture, it's something that I really love. So if you want those maps, them to you. So it's something that you have to know. So it's something that was compiled in the frame of the World Geological Map of the UNESCO. I don't know the acronym in English. What you have to know is that this is something that was 18,000 years before present. So everybody knows you get huge gaps, okay? So this is for high latitude system. You get a lot of growth belt with development of permafrost. So this was the case 18,000 years before. And what is important to have in mind is you get a major cooling what you got in mid and lower latitude is an increase of hot arid system. So it means that each time you get a cooling, you develop ice cap. What is the development of huge arid desert? And we will see what are the implications of this system. So if you look, what's going on 18,000 years before present, so, okay, so it means that the tropical, the one you have in different countries, so for example, taking the example of in Africa, it's almost nothing, the same in Amazon, and or wooded savanna, so it means something that is, yes, not a very dense forest in between. So what's going on? You have to imagine that this is the case 18,000 years before present, but it's what happened during the last year, at least during 19,000 years. So it was the climate status of the Earth. Okay, what's going on 18,000 years before present is what was the normal climate during the last summer. You understand, of course, that it has a lot of impact in terms of sediment production. So just to show you what's going on 8,000 years before present. So it's the period of Milankovitch cycle that corresponds to the hottest period of last 20 years before the human impact on the climate. So, and the landscape is fully different. The impact on that. So it's incredible how large is the tropical forests up to Senegal. It's called China. So, and the Sahara is a savanna, increase the temperate forest. Okay, so it means that the climate is really than the previous period, and this will be true for around 5,000–6,000 years before a change to other climate. And what should be happen if human activities occurring, we were supposed to be back to what was going on before. Okay, so this is really evolution. So again, I repeat, around 90,000 years duration. This is what's going on in terms of climate during the last climatic cycle. Okay. We have to look at 4 different modern source-to-sink systems, just to have an idea of the slope, what is erosional, what's the sediment budget. So to check for you what's going on, to measure, you understand, and you have in your order processes and the physiography in the modern sedimentary system. So just check or the queen of the source-to-sink system. So it's the Utra system in now. The second one that we have to check is the Congo. Okay, so is what the Congo, where is the Congo? So we will check on that. The third one, the Eastern Sahara and arid system. So this one is a hot humid, this one is a hand, and we go to a glacial periglacial one that corresponds to the St. Lawrence system of how different are those four systems, okay? So just a look to a DM of the Ganga-Brahmaputra system. So just to make the how to describe a DEM. So here you have a very nice of what the true mountain belt is here in the south. This is the Himalaya, and here to the north is a plateau where the Tibet. And what is very interesting is the comparison to the south, where you have Eastern Ghats and Western Ghats and Saputra range over there. That corresponds to a type of relief, okay? And those anerogenic relief are plateau as well, so different type of plateau, okay? This is anerogenic plateau, so degraded for this one, the decan. And so this is something that is important, different. To get a very nice example of a mountain range as well, the Indo-Burman system. And here you have a very beautiful example of submarine relief. So here is a zone with a trench over there, the Sunda system. And if you look here, this is probably mostly for accretionary wedge, okay, with few islands on top, okay. So here is the okay, and for the rest, you have the other example of what is submarine relief. You get here oceanic ridge, the Carlsbad Ridge, some transform, some relief that we have example of plateaus that are so important when we want to understand the ocean exploration that is part of the soil. That corresponds in that case to the 90 East Ridge and to Lac-Calif Ridge over there. So it means that with what I love is that you have an example of all the different type of earth relief, okay? Will change through time, so this is something that is important. And the interest on that system is to get also interesting rivers, the Indus, Ganga-Brahmaputra, we'll check about that, but we have among the largest Indus on this side, of course, the Bengal, and another one that is a little bit more little in size, that corresponds to the Nicobar fan, okay? So just to understand. So the one we have to look is the system in the world. So you have the DEM on one side, and you have on the other side the main feed. So if you look at the DEM, you have the catchment, okay? There, so this is the size of the catchment. You have two main rivers, highly controlled for the Brahmaputra. You arrive to one of the largest delta in the world. We will have a look to this delta. And here on the slope, you have a canyon, okay? You have a canyon, and the biggest fan in the world, the Bengal fan, that is quite sandy. So the recent papers, higher DP crews devoted to the study of the Bengal fan. So we have now a lot of information about. So you have to imagine the particles crossing the rivers, transported by the rivers, crossing the is located over here. So if we look, there are no depths that the Bengal fan, the place of ultimate deposition. So it means that when sediments arrive on the ocean, they cannot be transported beyond, except if they are oceanic currents, okay, where they can remove this. Okay, and the question is, here looking at the mountain range that is by rivers, so this is erosional. And the question is, what's going on here along the Ganga system? Is that something that is that a depositional system? So what's the nature of the system? Okay. This system, or in terms of sediment budget and spread. So this is a compilation made by Sommerfeld and Hulton. So those are the two largest rivers, the Indus. Okay, so if we talk in terms of ton by cubic meter per year, so we are among the highest values. So it's difficult for geologists to transform in terms of volume of sediments, but it's really the largest. And if you look, and this is a point that is debated, I will give a couple of minutes. So if you look at the solute, the same type of units, so it means that you have a very important sediment yield, but if you look at the solute, it's not so much. And this is something that we have to discuss this afternoon. So here's the profile. You get the profile of the Ganga and the Brahmaputra. So if we compare to this system, we will look at some systems. So it means that if you look, you get a convergence, and the seismic data showed that this really deposition after between the two rivers. When you are here at the base of what we call the lesser Himalayas, is strictly erosional, and here in between you get something intermediate between bypass to erosional system. Show you a geological section. There are few. So it's really one of the largest. So probably that the base sediments are metamorphic just of the loading. It could be a schist fascia. You get yes, more than 50 kilometer of sediments since the collision. Okay, this is what is interesting. Just in terms of sediment source, and this is something that that is important. So here's the Tibet Plateau, here's the Mount Everest. And what is interesting, if you look, and this is something that you can easily recognize, is that you can see, looking at the anticline made of sediments, that corresponds to the former fallen basin that has been folded and inverted, corresponding to the, and you have two main thrust, the main boundary thrust and above the thrust. Okay? And what is important for you is to know that. So I will start with the third example, that is a very arid one. That corresponds to the western Sahara. So I don't know if you're familiar with the topography of Western Sahara. This is a marvelous place. I've been many times. So to the north, you have in Tunisia, Algeria and Morocco, the famous Atlas Mountain. And you have here the Ogar Mountain that corresponds to a volcanic province related to a plume, a superficial plume, okay? And you get different erg, okay? The most famous one being the Great Western Erg and the Erg Chech here. And just to mention that the place where the Exons people developed in 1977 the concept of sequence stratigraphy were based on data, on published data on this margin that corresponds to the catchment of what we have to look at. So the Tantan margin that is located over there, okay? So if you look at the famous Northwest Africa sections of Exons, it's coming from here, okay? So imagine that the basement, the catchment of this system is what we have to look at. Okay, so here is the catchment, okay? And here is the river. And what is amazing is that this river today does not exist. So it means that this is something that was active during specific humid period of the evolution of this area. So it means that most of the time, this system is not active. It's dominated by Aeolian sediment. So it means that I anticipate a little bit about what's going on, is that in that case of this catchment, we will have an alternation of two types of dynamic due to climate change, one corresponding to a true fluvial activity, another one corresponding to wind activity, and with different issues in terms of sediment distribution and sediment production. And we will not talk during those 4 days about Aeolian transportation. There are a few models available about that, but I insist about the fact that this is something important in terms of sediment distribution and sediment characterization. And for example, the understanding of the climate change at the end of the 20th century was based on the amount of Aeolian dust in the high ODP wells. So it's the way that people discuss the climate change, and this is what is used now, talking about the dynamic of the monsoon. So it means that this is something very important. And what is interesting is that in that area, we don't have really deep sea fan. What you have is something that is also important in terms of source-to-sink dynamic. It's the current generated by the thermohaline circulation. You know that you have a deep and an intermediate circulation, and what you look here is the deep circulation generated by the Central Atlantic deep current. Okay, and you get this kind of loop, and whole sediments are reworked by this current, and there are no real deep sea fan. And talking in terms of sediment budget, this is a point that have to be taken into account when you do sediment budget. So it means that sometimes the ultimate deposition is not the deposition in the deep sea fan. That might be the reworking by those oceanographic, deep oceanic current. And at the moment, we have no idea about the efficiency of those current. We don't know if it is an in-situ reworking, if we can be able to transfer sediments over hundreds or thousands of kilometers. It's really something unknown, and unfortunately, something that would be nice to know. Okay. Okay, just to show you the difference between the DEM and the Google Earth image. So you clearly recognize the agar, and you see that here this domain here corresponds to an Archean craton called the Riblat craton. Okay. And the river is crossing and cutting through this craton. Okay, and if you look, and this is the next slide, sorry, this is the next slide. Yeah, in that zone, what we have is mainly wind activity with the Sansi over there, with Reg over there, and with ribbon dunes over there. And these record the direction of the trade winds, alizé in French. Okay, so you can know perfectly the direction of the wind. Okay, and this is the modern dynamics. So looking at this catchment today, this is Ionian activity. There are no fluvial activity at all. Okay, so if we look at the profile, again, this is amazing, and this is a characteristic of all the African rivers, is that it looks like a plain, but in fact, this is a plateau. Okay, so again, you have a local base level. But what is interesting is that we have here, along the profile, you have holes. Okay, if you look, you have holes. Okay, so it means that this profile is locally interrupted by those kind of holes. And what's the origin of those holes is wind activity. So it means that if I do a zoom of this area, you have hard rock over there, or hard rock, the wind is moving this way, and locally between hard rock, you generate cells, okay? And those cells scar the rocks, okay? And you get in the middle of those fluvial system, what you have is a large depression that can reach for the deepest one, something that is more than 100 meters deep. And what is interesting is that because of the erosion and the quality of the groundwater, what you have in those holes is deposition of salt water. It's not deposition, you have salty water, and those salty water generate evaporates, okay, and those depression became salty lake, and what you get by the end is salt. And maybe you heard that Targis in that area using camels, and I see them many times in that area, travel exporting big pieces of salt. It's coming from those depressions, okay? So this is the system. Okay, so it means that in that system, because of the chemistry of the groundwater itself reflected the dynamic of the past weathering of this area, you can get conditions to generate evaporates and to get salt. Okay, so again, you see how complex could be a source-to-sink system. You can get a fluvial component, you can get an aeolian component, and superimpose on that because of local geomorphic and for air groundwater chemistry conditions, you can generate oceanic rocks in the same system. Okay, so it's to show you the diversity of those systems. So here the same place at the time of a storm. If you a chance to be in a desert here during March, April, you can get those severe storm full of dust. So that's a very nice experience. And what happened is that all this dust is moving from the Sahara to the sea, Okay, here another example of this system. Here you have the same in the sea, so it's really like that. This is a wall of dust when you get that kind of storm. And if I'm back, and this is something that is crazy in terms of sediment budget, so it means that here all along the margin, from here, southern Morocco to Mauritania and part of Senegal, all the sediments of the margin are not fed by rivers, but fed by those storm made of dust, okay? And then all the fine-grained sediments are coming from the Aeolian dynamic, okay? All those particles are travel across the Atlantic and deposited by settling, okay? And the amount of sedimentation is not ridiculous. So it's what I want to insist on. So it means that you get regular amount of sedimentation. It's not so high, but you can get a few centimeters per year in some places, okay? So that's, but by the end, what you have is only fine-grained clay to silt sediments on this margin. It's quite difficult to get any evidences of sand, and this is really the dynamic that we have, okay? So if, again, I look at the climate change, so it means that this system is arid during 90,000 years, and during the Eocene, you get enough water to get those rivers active, okay? So it means that the estuary of the sedimentation, again, is sand accumulation, okay? Sand accumulation due to Aeolian dynamic during the glacial stage, and briefly and shortly, you get fluvial dynamic at time of the climatic optimum. So it means that during a few thousand of years, you get rivers, you fill the holes, you get evaporation, and it's really something that is brief again, and in between, you get this kind of Aeolian deposition. But if I'm back, okay, those Aeolian sand, most of them were provided by the reworking of older Aeolian deposits. So it means that you more or less rework the same amount of sediments. The only limit of that budget is the amount that you transfer to the sea. Okay. So now we have to look at the last one. Okay, this is the St. Lawrence. So this one is exceptional for different reasons. So I hope that most of you know that this place, just to make sure you know about the geography. New York is somewhere here. Washington is, so this is the Delaware, so somewhere here. Chicago is over there. Montreal is there. Quebec is there. Okay, so this is was covered by the ice up to 14,000 years, and again a little bit froze, and total melting at 12,000 years. Okay, so this is what's going on. And if we look at the source-to-sink system, so the catchment is quite narrow. Okay, you get a very nice deep sea fan. Okay, the Titanic is located somewhere here on the slope of Nova Scotia. Okay, and if you look, it's quite difficult to talk about a river. It's really here that you have a river from the Ontario Lake to Quebec. And here, just a connection of lake. So it means that defining a river is something that is meaningless, okay? just to show you what's the upstream part. So it means that this is scars located at the border of the ice cap, okay? And of course, all those lakes are buffer zone, okay? So it means that all the sediments, coming from the reworking of glacial deposits are stored in those lakes, and the shape of those lakes is directly the inheritance of glacial dynamics. Okay, so if you look, Erie Lake is quite shallow, Ontario is deeper, and the deepest one is Lake Superior. Okay, so it means that the contribution of this lake system to the global budget of the global budget of the St. Lawrence will be zero, okay? And on the other hand, and it's absolutely marvelous, okay? So the St. Lawrence is offshore a very nice glacial valley up to the shelf break, okay? This is the same for the Scotia embayment, okay, and the Bay of Fundy, so all those system glacial structures, okay, and here the river is just reworking during interglacial stage all the product of erosion of sediments that were formed during the glacial history, okay? So amazingly, and this is something that is really interesting and poorly understood, is that the amount in terms of sediment budget of the St. Lawrence is very low, and I explain you why. Is that most of the sediments are stored in the 7 lakes upstream of the St. Lawrence, so it means that the contribution at the end is only the reworking of this Quebec part of the system. So it means that this is this part that provide the sediments of the St. Lawrence. And amazingly, but this is also the case, we'll be back on that this afternoon, is that the amount of solutes is very important. So it means in terms of chemical budget to the ocean, it's something significant, okay? And the explanation is quite easy, is that to get hydrolysis, you don't have necessary to have hot water. What you have to have is water, okay? And then you can, even in high latitude system, get quite intense weathering and solutes production, okay? So that's my preferred profile. the river that does not exist. So again, the Brahmaputra, just as a reference. So if you look, the profile of the river, if we can use the word profile of the river, corresponds to the Great Lakes. So it's typically the profile of glaciers that were connected by lake. Here are the Niagara Falls, okay, and it's really becoming a river at the end of Ontario Lake. So this is Ontario, this is Erie, and so this is a very specific system. So the climate history is very interesting. So it means that again, during the last glacial maximum, you have to imagine an ice cap covering part of the Atlantic, okay? New York is under ice, Chicago is under ice, and this is what's going on during, all the glacial stage, okay? So, and this is only during the interglacial stage, so it means around 10,000 years that you get the dynamic, okay? In the case of the St. Lawrence, the chronology is quite well known. So it means that we have no record in the deep sea system. We have no record of the early glacial stage. So what we have is only evidences of local melting of the base of the ice cap. It's what is recorded in the offshore drillings, okay? And the place that is really critical is the melting after the last glacial system, where you get an incredibly high amount of sediments. That is the reworking of all the remnants of glacial erosion by the rivers, okay, and you store plenty of sediments in the lake, and of course in the St. Lawrence Delta, okay. The St. Lawrence Delta is mainly made of mud. Okay, so that's a muddy system, same for the deep sea fan. So it means that we get muddy system. Okay, so that's it for the different type of systems. So it's 11:45. So just what I want to convince you is the diversity in terms of topography, geometry, type of sediment production, okay? So that's very important. And again, you will use, and this is the regular rule, very simple profile for the modeling, the understanding of the processes, but keep in mind that your future might be to work in an industry where you will have to work on real systems, and what you have really to think about is the diversity of the system, okay, and the diversity and the importance of climate variation. So this is really the point that I want to emphasize. So I already insist about that. So this is the difference between alluvial fan and mega fan. So I will go faster, so we don't care about that. So that's fine. So just talking briefly about deep sea fans. Talking about deep sea fans. So deep sea fans are probably the system that are not very well worked. The only people working really on those questions are Mike Kovold and all those colleagues working on those systems. So really, a deep sea fan, it's something that is quite simple. This is a channel with levees and lobes, okay? So that's it, okay? So what's the change in that for some of them, the channel could be the only element available, okay? Or in other one, this is mainly lobes, okay? And what is very, what is changes is the distance from the slope of deposition and the grind size. So it means that what can change is the ratio between lobe and channel, the distance between slope and the end of the lobes, and the grind size of the system. So those are the three parameters. So it's well summarized by those old sketch, but I really love them. Okay, so between a system where everything is stacked along the slope. So here in that case, this is coarse grain, but that could be the case of the St. Lawrence, where even it's made of mud, it's really stacked on the slope. It's a system that could be made of channel and lobes, and made of sands that might be, for example, the Bengal, but the distance is very important, and that might be the Congo with channels and a little amount of lobes. And then at the moment, we got trouble really to understand what we call the transport efficiency. Why are there some system? So if you look, the Congo and the St. Lawrence are both muddy system. Okay, one you get exportation, the other one you don't get exportation. So it means what are the parameters that explain the efficiency? So the ability to transport sediments by turbiditic systems over great distance and with an idea of the grind size. It's really something challenging. We have some ideas, but honestly, it's something that is poorly understood, and it should be nice in source to sink system to understand what's the cause of this exportation. And again, I repeat, in the case of two mud-dominated systems, in what case the Congo you get exportation, in the case of the St. Lawrence you don't have exportation, okay? So this is this concept of transport efficiency that was developed by Emiliano Muti in 1979, but beyond that we have no clear idea. Just now we will change, and I just want to show you that the Earth's topography and then the source to sink system in the past were probably very, very different than the one today. Okay, and this is really something that I want to insist on. And yeah, it's really what is important. And I really like this map. This is not an official map. This is, you know, the company Robertson. Robertson is paid to do a global synthesis map. And what I like really in that one is that they do not try to put fancy topography, just data, okay? And if you look at what's going on, we are looking at per Jurassic, Oxfordian, so it means that we are around 160 million years, okay? So if we look at the topography of the Earth, what we have is mainly arcs, okay, insular arcs, so it means you get subduction here. Okay, so what you have is not Cordillera. The only place where you get accretionary mountain is in China, and those one were remnants, but everywhere this is arc. Here you get the Mongol-Okhotsk Ocean. There are debate if it is arc or not at the moment. But what is interesting is that this period is a period where the topography is very flat. You get evidences of weathering, red sediments, red clay sediments accumulation in Gondwana. And what is gray here all around, even here in the future Central Atlantic, what we call the Tethys, the Atlantic Tethys, okay? This is made of carbonate. So I mean everywhere, all what is gray is made of carbonate. And then you have to imagine at the late Oxfordian and Jurassic, okay, and Earth, that was really flat. We don't know mountain at that period. We have just remnants. Yeah, weathering everywhere, red sands, carbonate platform, something that is very different than today.
François?
Yeah.
Excuse me, what's the reference of the Robertson 2005 paper?
This is something that I got from Robertson, but they were public. I can send them to you and to put them in the intranet. Okay. For everybody, but it's public, so it was not really published. You know how behave those companies. Yeah, it's something that you can use. Mentioning Roberts. Okay.
Okay. Okay. Thank you.
So, in the frame of French research project on relief in France, we were with Cécile compiling the age of all the growth of all the modern Earth relief, and this is this boring table. So you get Central Andes, Paraná Plateau, Sao Francisco. So you get all the relief of the Earth, and for example, the Andes, you have the different stage of growth of with Peruvian, Incaic, and Quechuan phase. So we did that for all the relief of the Earth, and what is amazing as a result is that the major modern relief of the Earth occur during late Cretaceous time, so it means around 80 million years. That is a critical period in terms of plate kinematic and so on, but also thermal change of the oceanic lithosphere. So it means that this period is really something critical. So it means that we have really two different worlds before and after. So it means that all the modern world is a post 80 million years creation. So we can get evidences of all relief in Australia, and we were dating in Malawi weathering of Devonian age. So it means that they exist. They are on the Earth, very old relief. You have also evidences of deformation that are related to the closure of the Mongol-Okhotsk Ocean, so the Mongolian orogeny in the Broadway. But if we look, most of the modern relief of the Earth were quite recent features, a two-step history, okay. One around 80 and one around 40 million years, okay. And if we look, and I'm back to old geology, but I'm really proud to confirm that kind of approach. You know that they are famous, just to have the picture of this guy in the back. They are famous geologists. The first one is Suess, Edward Suess, who did the first synthesis of the geology of the world in a famous book, Das Antlitz der Erde, The Face of the Earth. And this guy understood that there are period of plate deformation. They were not using the term plate, but they were talking about global deformations. Even there are ranges. This is not something that is a snapshot. It was worked again by Stiller later, and the last one was Peter Ziegler, who did that kind of synthesis. And honestly, working in the basin, in Europe, in Africa, it works quite well. So it's clear that there are major period of plate kinematic reorganization leading to stress changes of the lithosphere, leading to vertical movement that could be in one place related to compression, in another one to strike slip, but that corresponds really to global event. And one is key for the Earth of the relief. It's this event that occur around 80 million years. That is a major change in plate kinematic. Okay, that corresponds to what we call the Subercinian Silurian deformation. Okay, and you get plenty of those. So this is really something that it is interesting in terms of global plate deformation, change of basin dynamic, relification, and then sediment routing system. And this is one of the things that we would like to test with Takis working in Tunisia, is to have a look of what is going on with the Austrian, the so-called Austrian deformations. So again, the Wilson cycle is of great importance to understand the global evolution of the Earth topography and then the evolution of the source-to-sink system. So you know that the Wilson cycle is an alternation of supercontinent and splitted continent. We define a divergence and a convergence, okay? And it controls at the first order the global distribution of the sedimentary basins, but also the Earth topography, okay? So today we are in a period of convergence. So what would be the next step to get a full convergence is the closure of the Atlantic. That's not yet the case. But for example, if you back to past geological time, Jurassic, and Cambrian Ordovician, you have a real flat earth. So it's really what I want to insist on, and related with specific system that I want to show you in a couple of minutes. So the global supercontinent or big continent is known. So we have Pangaea. Gondwana is not really a supercontinent. This is a superplate that is just prior Pangaea. The other supercontinent is Rodinia, around 1 billion years, and Columbia before. Okay, to do source-to-sink studies for Rodinia, I think that based on the archive, there are not so much things. But again, I repeat, working on Paleozoic and Mesophanerozoic system, it's really something that we have to keep in mind. Just to illustrate that, talking about past source-to-sink system, I will take an example of Gondwana, 480 million years. So it means that this is a period, a critical period in terms of plate dynamic. And this feature is very interesting. This is a reconstruction of the paleogeography, and we have enough archive to make sure that this makes sense. To see something with no equivalent today is to imagine that you have a continent with a shallow sea. This is the shoreline, with a shallow sea over a width. So if you look here, it's around 3,000 kilometers, 2,000 kilometers. So it means shallow marine system with no modern equivalent, okay? It's not the North Sea or the shelf of Argentina that might be equivalent to that kind of system. And in the back, what you have is very flat system, okay? Very flat system. And we have very nice archives of those sediments, okay, going from Mauritania, Algeria, to Saudi Arabia, and in the south. This is the famous, when we will go to South Africa, Table Mountain in Cape Town is an example of this system. So how it looks like. So here is the zone of unlap of those margins. So again, I'm back to that. So it means that the marine continental transition is somewhere here in the middle. So this is a place where you get deposition. So this is post-Paleozoic deformation, but you have to imagine that all this domain is subsiding. The boundary between marine and continental is over there. This is the unlap. And the same story on the other side. A lot of paleoccurrence measurements indicated the constant direction of river migration, okay? Okay, so I don't know whether I'm back. And if you look at this picture, it is sand, 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 and sand, okay? Few silts, no clay, okay? And you can take your car and to drive. This is the same fasces. This is Table Mountain in Cape Town, okay? And this is a kind of system that is amazing. And when you look at the fasces, what you see is evidences of 2D and 3D mega ripples with nice avalanching structures. No fossils, no bioturbations. At that time, there are no soils because it's before the terrestrialization, okay? So, okay. And then we have to imagine large break plane system. It's better to say bedload type channels connected one to the other one. And I try to find what are the largest braided system that corresponds to the Parana and the Ob in Russia. But you have to imagine that over distance, because what is amazing is that we have no real evidence of fine-grained floodplains in between. Okay, so it's really something that is really amazing to imagine that a full margin might be a sandy bedload river system. Okay, so we found some marine evidences. So it means that this system is regularly flooded by the sea with these marvelous bioturbation, Cruziana, Scolytos, plus evidences of nice tidal environments. Okay, and this is something that is unbelievable for this very scary place, but you can be in Saudi Arabia, you have exactly the same, and in Afghanistan as well. There are some evidences of those deposits, not flat, of course, deformed. Okay, so just to show you that those kind of systems were existing in other period, but with not the same extension. Okay. And this is one of the things that we have to work on. And so this is in Albian time. So here in North Africa, we have what we call the Nubian sandstone. Okay, so from Somalia, you get them up to Morocco. And the Nubian sandstone in the same story. So it means that what you have is sand, 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 and evidences of bedload rivers interfering with tidal deposits and over distance that are really incredible. Okay, and then we have that kind of landscape many times in the Earth's history. We have it in the oldest sedimentary basin in the world, Barberton. We have it in the Witz Basin, the Franzvillian. So it means that we have it many times in the geological time. So if you imagine, so this was made in frame of a project. Imagine the topography. So everything is depositional. If you look the zone of sediment feeding, there are few areas available. So is that reworking how it works? But it's a very in the frame of a very flat, Earth, very different than today. Okay, so this is what I want to insist on. Okay, so what time is it? Yeah, 25 minutes left, sorry. So what are the factors of source-to-sink changes? So the first is climate, the second is tectonic. Sébastien and Jean will talk many times about that. And I just briefly show you a couple of evidences that are important. So they control a STASI, okay? And I don't want to talk about the STASI. What I propose, because of the COVID and the fact that we cannot be all together and that you have to know each other better, is that the group of 15 ESR, you have to work together on a STASI, okay? So it means that you have to manage by yourself to read papers and to have a common view of a STASI. So it means that will be a way to meet you, of course, virtually in the first step, but to have discussion together and to know you better each other, working off a key question that is a STASI. What means sea level variations? You know, it's really highly debated at the moment. Probably the only things that you know about a STASI is the arcs, the Exxon's chart. Okay, and you know that with mantle dynamic at the moment, we don't know so much what's a STASI. So I think that it could be a good way for you to know each other, working on the STASI, and you prepare a kind of report that we have to discuss together, or when we will be on the field for Dragonstone, or if the COVID situation is getting worse, somewhere in May by virtual conference. But I don't want to talk about the STASI. I think that for you, that's a good way. This is important to discuss all together, to share, to discuss. So it's what I propose. And I will send you a couple of key papers, and you will find, and you will try to do that. We will manage that with the triumvirate. We'll manage that in order to prepare the Dragonstone, if it is possible during the Dragonstone trip. Okay, so tectonic. So a point that I really want to insist on, and with Seb, we share a common culture about that, because this is a Rennes culture, is that there are a direct relationship between the wavelengths of the deformations and the curves. Okay, so this is something that is marvelous. So it means that looking at the wavelengths of a structure, looking at the wavelengths of a relief, we can infer a possible cause. Okay? Okay? So we define different wavelengths based on multiple of deformation: 1 kilometer, 10 kilometer, 100 kilometer, 1,000 kilometers. And I apologize, I put short everywhere. So this is short, medium, long, very long. Okay, so short, medium, long, very long. And these relate to something that is in the upper crust, for example, a décollement level that might be salt, that might be clay, for example, talking about the Jura Mountains. You see folds, and the wavelength is a few kilometers, and it's directly linked by the décollement of the salt over the salt. So it means that here you have a direct proof that the cause and the décollement level is within the upper crust. Okay, so medium wavelengths. So I will correct. Medium wavelengths is something that is related to a crustal structure. Okay, so long and very long. Correct that later. Okay. Do you see my screen again? Seb, do you see it?
Yes.
Okay, so so it means that this is the crust. I have French example, but I think that you don't know about that. Long wavelengths is related to the lithosphere. This is the processes of buckling or boudinage. Best example is all the plate deformation with a wavelength of hundreds of kilometers. And when you get very long wavelengths processes, the only thing, deformation, sorry, the only process that can explain that kind of wavelengths is mantle dynamics, okay? So it means that this is something that is a very powerful tool. We can discuss if it is possible to get mantle dynamic processes with a wavelength of a few hundreds of kilometers. That's possible, okay, based on the different type of model on mantle dynamics, okay. And just to show you an example, we're back to the Congo. This is a topographic section between Gabon to the west to Kenya, Somalia boundary to Kenya to the east. Okay, this is the topography. You recognize the Congo Basin, the East African Rift with the two branches of the East African Rift. And if I smooth the topography, okay, I can characterize here in thick red line a very long wavelength that has to be related to mantle dynamics, and everybody knows that below the East African Rift there are super swell, and that's the record of the dynamic of the super swell below Africa. And if you smooth the topography with the different type of faults, so if you look, you can recognize something that is long that corresponds to the rift itself and the rift shoulders. You get that for the eastern branch, okay, here for the western branch. So the rift is clearly something that is lithosphere scale. Is that okay for everybody? And you add fault, okay, that is short to medium, that has to be related to crust dynamic with decollement level somewhere in the lower or in the upper crust, okay? So I think that that's a very powerful tool to describe the deformation and very useful working on source-to-sink processes, because you can do that either looking at relief or basin, so source-sink system. Okay, so this is something that is very powerful. Okay, and the record is really sedimentary basins, okay, sedimentary basins. And in the case of the sedimentary basin, you know that there are different types with critical subsidence rate that you have to know. So this is something important. And the largest basins, intracratonic or sac basins, that are with a size of a few thousands of kilometers with very low subsidence rate of 1 to 30 meters per million years. It's nothing, okay, nothing. Okay, we record mantle dynamic, and all the other basins are, of course, because of their size and the subsidence, a record of lithosphere dynamics. Okay, that's something clear. So please know the order of magnitude of the subsidence. This is very important to understand the nature of the preservation of the sedimentary record. So this is something important. Just to show you, and I forget. So this, I don't like this picture, but this is the only one available. This is the synthesis of Bailey, published in 2012 in Elsevier. So you get everything. So what is in yellow is the margin, are the margins, passive margin. In orange, what is active margin, and in blue, all what is due to intracratonic basin or sac basin. So if you look, you get the largest basin in the world, that is the Eastern Siberian Basin, okay? No, the Western Siberian Basin, sorry, this is the Eastern. So the Western Siberian Basin, looking at the size, is clearly something that is of a few thousand. This is mantle dynamic. The same for the Congo. So if you look at the size of the Congo, it has to see with mantle dynamic. If you look at the Michigan, it's something that has to see with mantle dynamic. Okay, so it means that you can relate the geometry, the size of the structure and the basins to something that is the dynamic. Okay, that's all for the tectonic. You will have plenty of illustration on mountain belt, okay, discussion about mountain belt, how climate to deformation, what's the impact. That's not the topic of this introduction. The climate. So I apologize, the year is not correct. Okay, so this is something published by Scotties. You know our work, Chris Scotties. Scotties is one of the specialists of the global paleogeographic world scale paleogeographic map. But unfortunately, he published not so much. So it means that it's very difficult to know what are the sources of the data. And I really love this one. That's very good because it tried to quantify the global temperature of the Earth. Okay, so I repeat that today we are the mean Earth temperature is 15 degrees. Okay, and you see that he proposed that at Triassic time, that might be probably the hottest period of the world, the mean Earth temperature may be around 28 degrees Celsius, okay? So it means mostly the double of today, okay? So it's something unbelievable. So you imagine what could be the dynamic of the Earth. So at that time, and of course, you know that everywhere in the world, when you look at Triassic sediments, they are red, okay? You have plenty of Aeolian deposits, evaporates, and hence on. So it's really clearly a crazy period in the world. So everybody agree about that. So everywhere you go, everywhere you found red sediments with fluvial and Aeolian plus evaporates. So that's same story in the Middle Devonian. Everywhere in the world where you go, what do you find? Carbonate and reefs. Okay, so that's something that really makes sense. Okay. Okay, for that, here I'm a little bit more skeptic. I have no time to discuss why I'm skeptic, because there are some data, and everybody agree about the main the main high south period. The Ordovician, my experience with the glacial Ordovician, the Ordovician glaciation is that it started during the middle Ordovician, then a little bit earlier than what he proposed. The same for the late Paleozoic glaciation. He only focused on the last evolution of the glaciation, but the glaciation clearly started during late Devonian time. Okay, so it means that this is very interesting, but again, it can be done better. So what is important for you, young SR, is to imagine that most of the history of the Earth was made with no ice at the pole. Okay, so that's what is important, okay? And if you look at some of the Scottish reconstructions, Markwick reconstructions, all the climatic data available, for example, for the Triassic, what they propose is that at the pole, the northern pole, okay, the temperature was in winter, so it means that the maximum something that was at temperate. Okay, so it means that a kind of Mediterranean climate, so something that is really unbelievable. Okay, so it's, I shown you that the topography of the Earth changed, and now what I show you, and that is important, is to think with very important climate change. So it means that the modern systems are very nice to understand the dynamic, what happened, but it's really important to keep in mind that the topography of the Earth, the distribution of the basin, and the climate change a lot, and that in the past the systems are really very different. So just to show you something that you probably already know, is that here is the delta O18 word synthesis of the benthic foram. So it means that you get both the water temperature plus the salinity. So it means that this is something that is not only temperature. I repeat, this is deep water data. But whatever, what you have observed is the famous PETM that probably Seb will talk about, to something that is a hot period of the Earth. You decrease and you move to the ice house history with a major re-heating during Middle Miocene that it works get that well. And what is important, okay, is that around 2.6, okay, and around 1. So we will do mean values. We get incredibly strong climatic changes. In the first one, we got related probably to the growth of the relented large ice cap. an increase, a forcing of the obliquity cycle, and later about the eccentricity cycle. Okay, so this is something that is the signature of the Pleistocene. And what is interesting is that in past glaciation, we don't have the equivalent of that. So if you look at the archives of the snowball, so they are polydated, the archive of the late Ordovician or the late Paleozoic glaciation, you don't find this kind of high resolution glacial, interglacial system. So it looks something that is very, very specific to our glaciation. Okay. So again, the conclusion will be that we are in a unique period in terms of geological evolution. Okay. So just to show you, and because I need this one this afternoon. Okay, 5 minutes. If it's something that I really like. So this is a compilation that was made by Morley based on pollens and woods. Okay, so of the distribution based also on the bauxites, on the evaporites, for the early Eocene and the distribution of the famous megathermal forest. So that implies that during all the months of the year, the temperature has to be higher than 80 degrees. Okay, so if you look at the distribution, and I had a paper in a frame of a project led by Cécile Robin, they found this kind of association in a high ODP well on the pole in the Lomonosov Ridge. So it means that if we look at that, we got in early Eocene a crazy Earth. So if you look, Asia is quite arid. Okay, the same here in northern Argentina. Okay, but if you look, you get everywhere, and mainly in Europe, so you know that they are that kind of system. You have to imagine very hot, humid conditions up to the pole. Okay, so, and this will have, of course, a lot of implication in terms of source-to-sink dynamic, in terms of sediment production, in terms of global chemical budgets. So it's really something important that you have to think about, and we will discuss about that this afternoon. Okay, so this, it's already made. So that's time for conclusion. Okay, and to have a lunch, even confined. So what I want to insist on is, first of all, the diversity in modern system of source-to-sink system. Okay, okay, the importance of the topography and so on, and in the case of the modern system, the change of the climate driven by the eccentricity cycle. Okay, so that's of primary importance for the modern system. But what we have in the past is really different than what we have in the modern system. Okay, so I repeat, we are in terms of tectonic in the convergence period of a Wilson cycle. So it means that we have a mountain belt growing, and this afternoon I will show you, talking about Europe, that we got an overall uplift, and that erosional system are dominant, and there are few depositional systems. Okay, this is one of the characteristics of our period, and this is the case in all the continents. So it's really something dominated by erosion. Okay, and in terms of climate, we are in a ice house period, and there are discussion, but probably 5-6 million years, we are in a bipolar glaciation. So it never occurred before. So that's the first time that we have a bipolar glaciation. Okay, one Antarctica, Antarctica. And we have something that is also, it seems unique in terms of geological history. It's a forced 100,000 year cycle since 1 million years. Okay, so it means that we have really to think differently about the past and the future. Even the processes and the way the system behaves is of course the same. Okay, so it's really what I want to tell today, and I will find another place to talk about the applications of source to think to sustainable environment. I will talk about that another time. So I will find a place for that. So I apologize. So that's it. Okay, that's it. It would be better to be together and to have discussion and so on. So okay, so it's a one-way talk. Okay, so if you want to have discussions, we can have discussions later. So if you send me a mail and we can have a chat or something. And again, organize you by yourself. So it means that you have to be now in connection. Say, oh yeah, he talked about that, but yeah, it would be nice. Maybe I'm skeptic because what he said, there are really arguments for. Okay. And so please, you manage to send me a mail and to ask for a discussion, or we open. So I know, so I did now many courses and by e-courses, and this is all the time the same story. That's a one way. I talk, I don't see the face of people in the front, so it's really the major limit. So feel free to ask me questions. And this is not the most convenient way to discuss about that.